In this video, we're going to talk about solving compound inequalities. I know what some of you are thinking. What do you mean by compound inequality? So let's say we have this situation. You decide that you're going to go shopping on Black Friday. You want to spend more than $50, but no more than $150. Anywhere in between $50 and $150 is great, but you don't want to spend less than $50 or more than $150. So how would we write an inequality to describe that situation? One thing we can do is we can start with this parameter. I want to be more than 50. So the total cost of what I'm going to spend, we'll say C, has to be more than 50, greater than or equal to 50. And at the same time, because I have no more than 150, so I want to be greater than or equal to 50, and at the same time, I want what I cost to be less than or equal to 150. So that's one way that I could write this inequality for this situation. This is a compound inequality. It's connected with the word and. Compound inequalities can also be connected with the word or. Since this is connected with an and, we can write it as one statement. We could write it as this statement and this statement, or we could combine it all together. We could say C in the middle is less than or equal to 150, and at the same time, and then read this way, C is greater than or equal to 50. Either one of these answers works. They mean the same thing. They're both compound inequalities. Our definition for compound inequality says consists of two inequalities connected by the word and or. One thing you're going to be asked to do is you're going to be asked to write an inequality that represents a set of numbers. And here we have it in a sentence as well as the graph. Here it says all real numbers that are greater than or equal to -2 and at the same time less than 3. This is what my graph would look like. I have less than 3, open circle, just like we did yesterday, and at the same time greater than or equal to, closed circle, 2. My variable, my x, is somewhere in between here. So I have x is less than 3, and at the same time greater than or equal to -2. So that would be my compound inequality. How about this one? All real numbers that are less than or equal to -3 or greater than 0. So this would be what an or statement looks like. I can either be less than or equal to -3 or I can be greater than 0. I'm not going to be both, right? And there's no number that's going to be in this shaded region and in this shaded region. These compound inequalities are a little easier to write because you use the word or. I'm going to start with this side and I'm going to say, okay, x has to be less than or equal to -3 or x has to be greater than 0. And that's how I would write my or statement for a compound inequality. To solve these, you solve these the exact same way you would the inequalities that we were solving the day yesterday. I take this, my compound inequality though, pretend for a second that this part was not here. What would you do? If you had that, you would subtract 3. Well, I'm still going to subtract 3, but this time I have really two sides of my inequality. So I'm going to subtract 3 from 7, and I'm also going to subtract 3 from 5. So that I go from the middle, from what my inequality, from where my variable is, I'm going to subtract 3. I'm going to do that to both sides. So -5 minus 3 would give me -8 is less than or equal to 2x plus 3 minus 3 gives me just 2x, less than 7 minus 3, and I get 4. From here, again, go to the center. 2x is in my center, so I'm going to divide by 2 because I want to get x by itself. So I'm going to divide by 2 here, I'm going to divide by 2 here, and here. -8 divided by 2. I'm not dividing by a negative number. My 2 is positive, so my inequalities stay where they are. -8 divided by 2 would give me -4 is less than or equal to x is less than or equal to 2. To graph this, I'm going to draw my number line exactly like I did before. I have two numbers here, so I'm going to start with my negative 4 is going to be on this side of my graph, and then I would be negative 3, negative 2, negative 1, 0, 1, 2 would be right here. I have x is less than 2, so I want an open circle at 2, and I'm going to be shading, I'm going to do this underneath so I can figure out where I'm shading exactly. I'm going to shade everything that's less than 2. But at the same time, I want to be greater than or equal to negative 4. So I know I want a closed circle at negative 4, and I want to be greater than or equal to negative 4. This is an and statement. Remember, and statements, both conditions have to be satisfied. I want all of the numbers that are less than 2 and at the same time greater than or equal to negative 4. So if I have this shading for this one and this shading for this one, the place where they're together is in the middle. So the only place that I'm going to shade is in between those two numbers. It's an and statement, so I want both conditions to be satisfied. Number 3 says solve and graph 6x minus 5 is less than 7, or 8x plus 1 is greater than 25. This being an or statement, again, it's a little bit simpler because I treat each of these as their own individual problems. So I'm going to do 6x minus 5 is less than 7 first, so I'm going to add 5 to both sides. And then I'm going to divide by 6. So I get x is less than 2. I'm going to write my word or. Then I'm going to go and solve 8x plus 1. So I'm going to subtract 1. So I get 8x is greater than 24. Divide by 8, and I get x is greater than 3. Graphing this inequality, 2 would be here, 3 would be here. I want less than 2, so everything going this way, or I want to be greater than 3, so open circle again, and I want everything greater than. I still can check these. Again, to check them, I'm going to pick numbers in my shaded region. Remember, this is an or statement, so it's kind of like saying you can do your homework or watch TV. You can do one or the other, but you can't do them at the same time, not both. So if I pick, say, 0, it's only going to work for this one, but that's okay, because I want either this one to be true or this one to be true. Number 4, again, is our compound inequality. So I'm going to pretend this minus 3 and less than sign are not there. So what would I do if I was solving that inequality? I would add 1. So instead of adding 1 to just the 5, I'm going to add 1 to the 5 and to the negative 3. So it kind of looks like we have 3 sides, but we really don't. Negative 3 plus 1 gives me negative 2 is less than negative 2x is less than or equal to 6. So again, I pretend this isn't here. What would I do to solve that? I divide by negative 2. But remember, if I'm dividing by a negative number, I have to flip the inequality. So negative 2 divided by negative 2 is 1. This flips. Here I get x. This also flips. And then I get negative 3. Normally, I don't see inequalities like this. It's deceiving to have the larger number on this side and the smaller number on this side. For me on a quiz or a test, if you leave it this way, it's okay, but we really should switch this around so that it looks correct. My smaller numbers being read first and then my larger number. When I go to graph this one, same thing, open circle on 1. And closed circle on negative 3, I want to be greater than or equal to negative 3, this way. And at the same time, I want to be less than 1, so that means I shade everything in here. This one's a bit different. We have the park is 1.5 miles from your house. The mall is 2.25 miles from your house. Find the minimum distance between the park and the mall. Find the maximum distance between the park and the mall. And then we're going to write an inequality. So let's take a look at this. If I say my house is in the center here, and I know the park is 1.5 miles. So let's just say the park is here. That's not the only place the park could be, though. The park could be really anywhere on the circle with a radius of 1.5. So if I add my circle here, here's going to be my center. The park is going to be anywhere on that radius. Then the mall is going to be 2.25 miles away from my house. So again, it could be here, or it could be anywhere on the radius of that circle. So let's say it's here. And again, I'm going to draw that circle. So now let's do some labeling. I know that the park is 1.5 miles from my house, so the distance from my house to the park is 1.5 miles. I know the distance from my house to the mall, so that distance there is 2.25 miles. I want to know what's the minimum distance between the park and the mall. So the minimum distance between this icon and this icon. So if I take my mall and I move it around the circle, the minimum distance would be if I had a straight line going from my house to the park and then the park to the mall. So this distance here is going to be my minimum distance. So I'm going to take my distance from my house to the mall and my distance from my house to the park, so the radius of this circle and the radius of the large circle, and I'm going to subtract them. So my minimum distance would be 2.25 minus 1.5. Or in this case, 3/4 of a mile. Okay, well then what's my maximum distance? My maximum distance would be if I took this and put this mall as far away from the park as I possibly could. Well, if again my mall is anywhere on this circle, then my mall, to be farthest away from the park, would have to be on the complete opposite side of the circle. So to find that maximum distance, I'm going to add the 2 radii of my circles. And I would get a maximum distance of 3.75 miles. So now the question is, how can we write an inequality to describe all of the possible distances? Remember, I could have my park, say here, and my mall, say over here. Or my park here. I could have it anywhere on this. So how do I write that inequality to say, all right, any of those possible distances? I'm going to write a compound inequality. So I'm going to say my minimum distance is 3/4 of a mile. So 3/4 would be less than or equal to my distance, we'll say D, and my distance has to be less than or equal to 3 3/4 of a mile. I have to be anywhere in between here.